Hello audience, we are going to discuss about the topic of Laplace transform. The Laplace transform is of two types, bilateral Laplace transform, unilateral Laplace transform. So we will see the bilateral Laplace transform equation. So if we take a particular signal f of t, the signal f of t will have the Laplace transform capital F of s given by this integral minus infinity to infinity f of t into e power minus st dt. Now here S equal to sigma plus j omega is called the complex frequency parameter, and sigma is the attenuation factor, j omega it represents the angular frequency component. Now if we see the region of convergence, which is also called ROC, it refers to the range of the values of S for which the bilateral Laplace transform is a finite value. Now next we are going to discuss unilateral Laplace transform. It is given by this integral 0 minus to infinity f of t into e power minus st dt. Now this unilateral Laplace transform, it is applied to the causal signals because the time integral is from 0 to infinity. So which is the time that is applicable to the causal signals. Now again the ROC is the range of the values of S for which this unilateral Laplace transform will converge or will be less than infinity. So it must be a finite value. Such is the range of the S values, and that is called ROC. Now this ROC of the ULT will be right-handed, means it will always be like the real part of S greater than some number. Okay. Now we are going to do a simple problem. We will calculate unilateral Laplace transform of unit step. So we are going to take this Laplace transform formula and substitute u of t. We know u of t is 1. So we simply have to do the integration of e power minus st, which is simply e power minus st divided by minus s. Now we substitute the limits infinity and 0. So you are going to get e power minus s into infinity, which will be 0, and minus e power minus 0, which will be 1. And of course here we have the factor minus 1 by s. So we are going to get the final answer as 1 by s. So the ULT of the unit step is simply 1 by s. Now what is the ROC? The ROC is the range of values such that real part of s is greater than 0. Why? Why? Because if you see this integral here, once you substitute this infinity, this number is e power minus s into infinity. We have taken this number e power minus s into infinity as 0, but that will be 0 only for positive values of s. Therefore, we are taking the real part of s to be positive, which is greater than 0. That's all. Now next we are going to calculate the unilateral Laplace transform of exponential signal e power minus at u of t. Again we take this signal, substitute into the formula, and we are going to get the integral e power minus at into e power minus st dt. Now we can combine these two exponentials as a single exponential, e power minus a plus st dt. Now when we do the integration, we will get 1 divided by minus a plus s, and again the exponential function, and we are going to substitute the limits 0 and infinity, and then in the similar fashion, when you substitute infinity, the first term will become 0, and when you substitute 0, you will get the second term as 1. So therefore the answer will be 1 divided by s plus a. Now here again the ROC is given by real part of this factor a plus s, that must be positive. So the real part of s plus a must be greater than 0. So real part of s must be greater than minus. That's the ROC. Now we are going to see the unilateral Laplace transform of the exponential signal, which is e power plus at u of t. Now we are going to substitute the signal into the ULT formula, and we are going to get the integral e power at into e power minus st dt. Then you combine these two exponentials, and we are going to take minus as a common factor. So you'll get e power minus s minus at dt. And when you do the integral of this, you will simply get 1 divided by minus of s minus a as a factor, and then the exponential function again e power minus s minus at, and then you have to substitute the limits 0 and infinity. Again, when you substitute the infinity, this first term will be 0, and when you substitute 0, it will become 1. So the final answer will be 1 by s minus a. Now the ROC will be the real part of this factor s minus a must be positive, greater than 0. So the real part of s greater than a. Now using the two previous problems, we can calculate the unilateral Laplace transform of the sine function a sine omega naught t u of t. Now we are going to substitute this signal into this Laplace transform formula, and then we are going to get the integral 0 to infinity a sine omega naught t, and of course u of t is 1 into e power minus st dt, and then we are going to factor this sine omega naught as e power j theta minus e power minus j theta divided by 2j. Now we are going to get two integrals, and we are going to have two exponential factors as well. So we have to combine the exponential factors. So we'll combine here minus st and j omega naught t. These are the exponential factors, e power a into e power b, that will be e power a plus b. Now we are going to take the minus common, so you will get the integral, and this is the constant a divided by 2j, and then we are going to combine this e power j omega naught t with e power minus st, and we are taking minus as common, so you will get e power minus s minus j omega naught t. Then you here you have a minus sign, and you will get e power minus s plus j omega naught t by combining these two terms. Now, based on our previous problem calculations, we know when you do this integration, we are going to simply get this term as 1 divided by s minus j omega naught, and there is a minus sign here, and here when we do the integration, it will be whatever is this factor 1 divided by s plus j omega naught. Now when you do the cross multiplication and you simplify, you will get this answer a omega naught divided by s square plus omega naught square. Now the ROC, we are having two factors. The first factor is 1 divided by s minus j omega naught. For that, the ROC is simply, we have to keep the real part of this term as positive, like in the previous problems. So the real part of s minus j omega naught should be greater than 0. Now the real part of j omega naught will be 0 because there is j multiplied by omega naught. It's a purely complex number. So real part of j omega naught will be 0. So we'll get real part of s simply greater than 0. Now we have to see what is the ROC for the second factor. Now the ROC for the second factor based on our previous problems will be what? The real part of that factor should be positive. So the real part of s plus j omega naught, it should be greater than 0. So we'll get the real part of s again greater than 0. So the overall ROC is simply the intersection of these two ROCs, ROC of the first factor intersection with the ROC of the second factor, which are both are same. So the final overall ROC is simply real part of s greater than 0. Now we are going to discuss some of the properties of the Laplace transform. The first property is linearity property. So if we take a linear combination of two signals a1 f1t plus a2 f2t, the Laplace transform will be the linear combination a1 f1s plus a2 f2s. Now next we are going to see the time shifting property. So if we take the Laplace transform of the time shifted signal f of t minus capital T, we will get e power minus s capital T multiplied by capital F of s. So you are getting that exponential factor e power minus st in front of the Laplace transform. Now we will prove this property. It's a very simple proof. These proofs are similar to the proofs in the Fourier series and Fourier transform. The proofs are exactly the same. They have the same methodology. So we take this Laplace transform of f of t minus capital T. We write the integral. Now we have to substitute in place of t minus capital T m. Then dt will be dm, and you can write this t as m plus capital T. Therefore, this ult of f of t minus capital T we can simply write as the integral f of m and e power minus s t we can write as m plus capital T, and dt will be replaced by dm. Now we can take e power minus s capital T outside this integral because the integral variable is m, and henceforth we can simply get e power minus st into the integral f of m e power minus sm dm, which is simply the Laplace transform of f of s. So we are getting the final answer e power minus s capital T into f of s. Next we are going to discuss translation and frequency property. So we take the signal e power at f of t. For that, the Laplace transform will be f of s minus a. So the proof is straightforward. So we'll substitute e power at f of t into this formula. Then we'll combine these two exponentials, and we get the integral f of t, and you're taking s common with the minus sign. So you'll get e power minus s minus a t dt. Now this is exactly same as the Laplace transform. The only thing is in place of s you are having s minus a. So therefore this entire integral will be f of s minus a. Now let us see the next property, which is differentiation in time property. So if you take the derivative d by dt of f of t, the Laplace transform must be s into f of s minus f0 minus. Now we are going to prove this property. So we will take the ult of the derivative, which is represented as f dash of t. Then we are having this integral 0 to infinity f dash of t, which is simply d by dt of f of t into e power minus st dt. Now here we use integration by parts, and you are going to substitute u is e power minus st, and whatever is the dv, which will be this f dash t dt. And the integration by parts formula is integral u dv is equal to uv minus integral v du. So we substitute this integration by parts for this integration. Then we have to first write u and v. U is already e power minus st, and if you integrate this dv, you are going to get v, and here you are integrating the derivative of f of t, so you will again get here f of t, and then you have to substitute these limits, then minus integral v. V is again f of t, you have to write du. Du, you have to take a derivative of this. You will get minus s e power minus st dt. Now we can see in this first term, if you substitute infinity, you will get 0, and then if you substitute 0 minus, you will get minus f of 0 minus, because it is the lower limit, and here minus of minus plus, and we take s outside the integral, plus s, and then you are left with the integral f of t into e power minus st dt. Now what is this integral? Integral f of t e power minus st dt is simply capital F of s. So we are getting the final answer, s into f of s minus this factor f of 0 minus. That's the final result. Now using this differentiation property, we will calculate the Laplace transform of unit impulse. Now we know the impulse function delta of t is the derivative of the unit step u of t. So if you want to take the ULT of delta of t, the impulse, it will be simply ULT of the derivative of u of t, which is a step. Now we know from the previous property ULT of the derivative of f of t will be s f of s minus f0 minus, and we already know the ULT of u of t is 1 by s. So we are going to substitute this into this equation. So our f of s will be simply 1 by s. So the ULT of the delta of t will be the ULT of the derivative of u of t. So that will be this s f of s minus f0 minus, and in place of f of s we will substitute 1 by s. So you will get 1 minus u of 0 minus. Now u of 0 minus is the value of the unit step just before the origin, which is 0. So we will get 1 minus 0. So the final answer is the ULT of delta of t will be 1. Now we are going to discuss here a little bit about the integration property. So if we calculate the unilateral Laplace transform of the integral f of t dt, that will be capital F of s by s. Now here we are also discussing the differentiation by s property. So if we take the signal t into f of t, its Laplace transform will be minus d by ds of f of s. Now we are going to prove this property. So let us take the ULT of f of t, which is capital F of s, which is the integral 0 to infinity f of t e power minus st dt. Now we will take the derivative d by ds on both sides of this equation. Then we will get d by ds of f of s, and you have to take the derivative of this integral. So when you take the derivative with respect to s, integral and f of t and also d of t dt will be constant, and the integral f of t and dt, it will come out, and the derivative will only go and apply on e power minus st, whose derivative will be e power minus st, and now the derivative is with respect to s, so the constant that will come out will be minus t. You have to be careful of that, because you are taking the derivative with respect to s. So when you take the derivative of e power minus st, you will get e power minus st, and the constant that will come out will be minus t. So now we are going to combine this t and f of t, and then write this e power minus st dt, and of course we have a minus sign here. Now what is this integral? The integral is nothing but the ULT of the new signal t into f of t, and of course here we have a minus sign. So hence we get the final answer. The ULT of t into f of t will be the minus of d by ds of capital F of s. Now we are going to discuss little bit about the initial value theorem. The initial value theorem states that f of 0 plus is equal to limit s tends to infinity s into f of s. Now we will prove this simple property. So from the differentiation property we know ULT of the derivative f dash of t is, we are writing here the ULT integral 0 to infinity f dash of t e power minus st dt, and that is given by the differentiation property as s f of s minus f0 minus. Now we take the limit s tends to infinity on both sides. So the limit s tends to infinity of this integral will be equal to limit s tends to infinity of s into f of s minus f0 minus. Now when you take the limit s tends to infinity into this integral, you will get e power minus infinity. So this entire integral as s tends to infinity, the limit will be 0. And here the first limit will be limit s tends to infinity s into f of s, and minus, here in the second factor it's a constant, so the limit will not apply to this, it is a simple constant, so you will get minus f0 minus the constant itself. So from here we can write, since the function f of t is continuous, f0 minus, which is equal to limit s tends to infinity s into f of s, that will also be equal to f of 0 plus. Now we are going to discuss the final value theorem. It tells that limit t tends to infinity f of t is equal to limit s tends to 0 s into f of s. So now again we are going to take the differentiation property, which is ULT of the derivative f dash of t is equal to that integral, which will be s into f of s minus f0 minus. Now we are going to take the limit s tends to 0 on both sides of the equation. Then we are applying the limit s tends to 0 to this particular integral, and we will also apply the limit s tends to 0 to s into f of s minus that constant. So when we put the limit s tends to 0, here you will get e power 0 for this integral. So that will be simply reduced as the integral of f dash of t. Now what is the integral of the derivative? The integral and derivative will get cancelled. So the integral of the f dash of t will be again f, because the derivative f dash is cancelled by the integral. So again you will get f of t. And now you have to apply the limits, whatever is the limit of the integral, which is 0 minus and infinity. So the first term will be limit as t tends to infinity f of t minus f of 0 minus. Now we are going to the right hand side RHS, and the first term is simply limit s tends to infinity, s tends to 0, s of s into f of s minus the constant term f0 minus. Now both the constant terms will cancel each other. So we are going to get the final answer, limit t tends to infinity f of t will be equal to limit s tends to 0 s into f of s. Now we are going to discuss about the convolution theorem. The convolution theorem of the Laplace transform is exactly the same as the convolution theorem of the Fourier transform, and it simply states that the Laplace transform of this convolution signal f1 of t convolved with f2 of t will be the multiplication of the individual Laplace transforms f1s multiplied by f2s. That's all. The proof of this convolution theorem of the Laplace transform is exactly the same as the proof of the convolution theorem of Fourier transform. So we are going to take the ULT of f1 convolved with f2. then we are going to write the integral of that convolution multiplied by e power minus st dt. This is the Laplace transform integral. Then you have to write the integral for the convolution. So now we are going to get double integral. The first integral is the ULT integral. The second one is for this convolution integral. And you will get f1 of tau into f2 of t minus tau d tau into this e power minus st dt. Now we will write t minus tau as a new variable m, and we will get dt is equal to dm, and you have to substitute wherever t is there m plus tau. Now this ULT of this f1 convolved with f2 becomes this double integral f1 of tau. The second one becomes f2 of m. The d tau we are writing as it is, and here this e power minus st is there. The t will be replaced by m plus tau, and dt will be replaced by dm. Now we can factor this into two integrals. So we take all the variables of tau as the first integral, f1 of tau, this d tau, and we also take this e power minus s tau as the first integral. Now multiplied by the second integral, which is f2 of m dm and e power minus sm. So the first integral is simply capital F1 of s, and the second integral is simply capital F2 of s. Again, we have to remember these integral variables d tau or dm, they are simply dummy variables. Finally, they will be substituted by the definite integral limits. Tau will be substituted as infinity and 0. Similarly, m will also be substituted as m is equal to infinity and m equal to 0. So this is nothing but the Laplace transform capital F1 of s multiplied by the Laplace transform capital F2 of s. Now here we are showing you some unilateral Laplace transforms of some basic signals in a table. For the impulse signal delta of t, the ULT is 1, and for step function u of t, the ULT is 1 by s. For e power minus at ut, the decaying exponential, ULT is 1 by s plus a. And for growing exponential, e power at ut, the ULT is 1 by s minus a. And we are also having the values for the sine and also cosine signals. Now here we are going to discuss little bit about this pole zeros of the Laplace transform. So when we are calculating the Laplace transform, let us take the example. So if we see the Laplace transform, we can write it as a numerator divided by a denominator. And if we take the numerator as a factor, so we can factor it as s minus z naught into s minus z1 so on, divided by denominator can also be factored s minus p naught into s minus p1 so on. Then the roots of the denominator, they are called poles. So whatever are the roots of the denominator, they are called the poles, and at those poles the Laplace transform becomes infinity, and therefore the ROC cannot contain the poles based on this definition of the poles, because we have defined that the poles are simply the roots of the denominator, and therefore at the poles, that is s equal to p naught or s equal to p1, the Laplace transform becomes infinite. Therefore the ROC cannot contain the poles. Now what are called zeros? The roots of the numerator, that is s equal to z naught, s equal to z1, they are called the zeros. At those zeros, the Laplace transform will take the zero value. Now we will take a simple example of the Laplace transform. F of s is s minus 1 into s minus 2 divided by s plus 3, s plus 4, s plus 5. And here we can very clearly see that the roots of the denominator will be the poles. Therefore, the poles are P1 is minus 3 and P2 is minus 4, P3 is minus 5, and the roots of the numerator, they are the zeros. So therefore Z1 will be 1 and Z2 will be 2, and we can mark these poles and zeros on the graph sheet. And this is called pole zero plot. So we are marking Z equal to 1 here and Z equal to 2 here, and those zeros are marked by using a circle, small circle or a dot, and the poles are marked by a cross or a into symbol. So here we have marked these three poles. So this diagram is called pole zero diagram or pole zero mapping also. Now finally we compare Laplace transform and Fourier transform. So we have seen whatever is the Laplace transform equation f of s is the integral f of t e power minus st dt. Now if we see the Fourier transform equation, if we take f of omega, it will be the integral of f of t into e power minus j omega t dt. So if we put s equal to j omega in the Laplace transform, we will get the Fourier transform. So f of s where s equal to j omega, we are going to get the Fourier transform f of omega. That's the relation between Fourier transform and Laplace transform. So you have to substitute s equal to j omega in the Laplace transform, then you are going to obtain the Fourier transform. Now finally we are going to see what is a transfer function, and this transfer function is a very important topic. So let us consider a signal x of t, and let us consider we are having the impulse response h of t. Then the Laplace transforms will be x of s and h of s, and we know that the convolution signal x1 x of t convolved with h of t will have a Laplace transform which is x of s multiplied with h of s. Now if we consider the LTI system with the impulse response h of t and the input x of t, the output signal y of t we know is given by the convolution x of t convolved with h of t. Now if we take Laplace transform on both sides, for Laplace transform of y of t you will get y of s, and the Laplace transform of the convolution of x of t convolved with h of t, that will be x of s multiplied with h of s. Now we can write this function h of s as y of s divided by x of s. Now this h of s is called the transfer function, and it is the ratio of the Laplace transform of the output signal and the Laplace transform of the input signal. Also, the impulse response h of t is obtained by taking the inverse Laplace transform of the transfer function. Therefore, the h of t will be the inverse Laplace transform ILT of the h of s.